Thanks again for inviting me. And yeah, I'm excited to be here. This is sort of and pushing me to look at this topic because this was a new topic for me, one that I'm still trying to get my head around. And I hope that those of you here who have more experience with teleology may be able to help me out with some of the kind of more speculative conclusions I want to draw at the end here. So yeah, I'm going to be talking about the principle of least action and other similar principles and the role of teleology in physics. So I'll start by just saying, with this quote from Ernest Nagel, just giving what I take to be kind of the received view, that modern science regards final causes to be vestal virgins which bear no fruit in the study of physical and chemical phenomena. And because of the association of teleological explanations with the doctrine that goals or ends of activity are dynamical agents in their own realizations, it tends to view such explanations as species of obscurantism. So, in other words, final causes have no place in physics. This seems to be part of this sort of larger trend away from final causes in modern science, right? We can think of the birth of modern physics as a move away from final causation to efficient causation and its explanations. So, right, in the Aristotelian picture, we have things are made of certain elements. Those elements have their natural place in the universe, and that explains why things move the way they do. If something's made of earth, it's trying to get to the center of the universe, and similarly for the other elements, trying to get to their natural place. But of course, with Newton, we get forces, and forces are responsible for why things move the way they do. So here we have universal gravitation. Things move, things fall because they're affected by this force that's literally just pushing them one way or the other. Okay. Of course, there's some wrinkles in this narrative, right? There are some aspects of classical physics even that don't fit neatly into this mode of explanation. In fact, the example I just gave, the universal gravitation, already involves a little bit of a wrinkle when it comes to a mechanistic worldview, right? We have forces that are acting at a distance instantaneously in Newtonian gravitation. And we also have principles like conservation laws or symmetry principles that, again, don't neatly fit into the picture of causal explanation understood in a kind of mechanistic way. What I'm going to be talking about today is another one of these kind of wrinkles, various so-called variational or extremal principles in physics. And these have played an important role in the development of physics, and they still do. So I think it's an interesting case. And just to give you the basic idea of a variational principle, in general, the idea is to consider a range of possible values for some physical quantity and assert the value must be an extremum, that is, must be a minimum or a maximum. So for instance, if you want to know what shape is this chain going to take, it's secured on two ends, and there's a gravitational field here. We can figure that out by asking, how can we minimize the potential energy of the entire chain the whole way across? And when we do that, we can use this so-called calculus of variations to do that. We find this shape called a catenary, which is almost a parabola, but not quite. Just by looking at each point, there's no way to get a lower potential energy. Cool, so that's going to be the basic idea. Where does teleology come into this? Well, at least as a first pass, and again, I'm less of an expert on teleology than some of the others in the room here. So all I'm meaning, at least at the beginning here, is that the explanations appeal to what looks like a goal state. Like in the previous example, trying to achieve the minimum potential energy is one of the premises in the explanation. And in fact, we get quite strong statements of this. So here's a quote from Max Planck, who's one of the founders of quantum mechanics, talking about the least action principle, which is a variational principle. He says the least action principle introduces a completely new idea into the concept of causality. I guess it's not that new really, but moving on. The causa efficens, which operates from the present into the future and makes future situations appear as determined from earlier ones, is joined by the causa finalis, for which inversely the future, namely a definite goal, serves as a premise from which there can be deduced the development of the processes which lead to this goal. So here we have quite explicit connection between a variational principle and the idea of a final cause. Okay, so that's the basic idea. What I'm going to be talking about, the plan for the talk. First, I'll talk about a variational principle called Fermat's principle, or the principle of least time, then the principle of least action. And then I want to talk a little bit, very kind of schematically about Feynman's path integral formalism approach to quantum mechanics. And then I'll look at an assessment of where this leaves us with respect to teleology. And the reason I want to look at the path integral formalism is some have argued, some people seem to think that because that from this formalism, we can explain the principle of least action in a way that kind of diffuses its apparent teleological aspect. Okay, I want to push back against that at the end of the day a little bit. Okay, cool. So Fermat's principle. So 16, and I should say I'm going to proceed kind of chronologically, but I will be bringing in contemporary interpretation as we go, so not purely historical. So in 1662, Fermat demonstrated that light travels along paths that take the least time. So we assume that light travels along the path for which the resistance from the surrounding media is minimal. Then we determine the geometry, the trajectories for which the transit time is an extremum, a minimum or a maximum. And what's really cool is that using this principle, Fermat's able to derive laws of optics, in particular Snell's law. So here's the basic picture. We're trying to get from point A to point B, where there's two different media involved, let's say air and water. And Feynman's example that he uses when he explains this in the lectures is imagine you've got a lifeguard on the beach trying to get to someone drowning in the ocean. They're not going to want to dive straight into the ocean, presumably, if they're at A and the victim is at B. They're not going to want to go straight into the water. They're going to want to go along the beach for some period of time and then go into the water because it's much slower to swim than run on the beach. And light does basically the same thing. That's Fermat's idea. Okay. And yeah, as I said, from this, we can derive Snell's law, which says that when light is refracted, that is when it goes into a medium of a different speed, a different resistance, the ratio between the signs of the angles of incidence and refraction is a constant that depends only on the respective nature of the two media. So you can write it this way, where these are the signs of the angles that are normal to the boundary. These are the velocity of light in the respective media, and these are the refractive index of the medium. Okay, so here's a picture. Snell's law tells us how these angles relate, just based on the properties of those media. Okay, so we can, and so that's really interesting that Fermat's principle allows us to get this more specific law of optics. Now, it's not, the point that's very important here is that we don't need to use Fermat's principle to get this result. In fact, Descartes himself, as we see in this quote from Leibniz, Descartes himself has a way of deriving Snell's theorem using purely efficient causation. As we can see also from this quote, Leibniz isn't particularly happy with it, but the point here is that it's not indispensable. So is there any value to Fermat's principle? Well, yeah, I think that even if it's not indispensable, there's something to Leibniz's objection. There is something compelling about the explanation provided by Fermat's principle. What is that? Well, there's a value in explaining laws that we have with more general principles, right? We do this with conservation laws, like the conservation of energy. And you could see why someone like Leibniz would want that kind of explanation. We have to have not just a mechanical explanation, but where there has to be a reason for the laws, the underlying laws themselves. At least that's my vague understanding. So I think at this stage of the debate, at least, if Fermat's principle has a teleological character, this is doing some important work in our understanding of optics, again, at this stage. Okay, there's another thing that people often mention in talking about the principle of least time, or Fermat's principle. Even before going to quantum mechanics, we had a wave theory. Okay, first, why are we puzzled by teleology here? Well, here's again for Feynman from his discussion in his lectures on physics. And this is a really nice passage, so apologies for the long quote. The idea of causality, that it goes from one point to another and so on, is easy to understand. But the principle of least time is a completely different philosophical principle about the way nature works. Instead of saying it's a causal thing, that when we do one thing, something else happens and so on, it says this: we set up the situation and light decides which is the shortest time or the extreme one and chooses that path. But what does it do? How does it find out? Does it smell the nearby paths and check them against each other? So there's a kind of puzzle in how this could possibly work, right? How is it that the light could figure out the path of least time? So there's some resistance, at least again, anachronistically looking back on it, there's some resistance to this teleological element of Fermat's principle. And yeah, so now I want to get to the point that shortly after Fermat's principle, we have Huygens developing a kind of wave theory of light, has an alternative explanation. Okay, and this key idea here is that when a wave, so now we're thinking of light as a wave, when it encounters a disturbance, that is the source of a new wave, or little wavelets, these spherical waves. And then we add up all of these secondary waves, and then the result of that addition of all those little waves tells us the future direction of light. And we can, from this, we can derive Fermat's principle. So here's a picture of how this roughly works. So we can see when the light hits this boundary, we get all these little spherical wavelets. And then we can just sort of take the line that's tangent to all of them, and that's going to tell us which way the light's going to head. Okay, so this is at least looking more causal in the sense of efficient causation. However, the geometrical construction that Huygens used is provably equivalent to Fermat's principle. So there's a real question here about which explains which. So that again, the construction, by that I just mean this idea that the direction of light is determined by this line, this wavefront line. So this is at each time, W, W prime, W double prime. And we draw the kind of line tangent to all of these wave fronts, all these little wavelets, and that tells us the path of light. So if the light was at P, it would go to P prime and P double prime, etc. And this is just geometrically equivalent to Fermat's principle. So if you look historically, you see people who say, oh, Huygens explains Fermat, and then you have other people that say he presupposes Fermat in his construction. So at this point, again, I think it's sort of a matter of taste which way we take the explanation to go. Okay. So now let's go to the principle of least action, which is just kind of, in some sense, just a generalization of Fermat's principle. So in its modern formulation, which is due to Hamilton, it asserts roughly that a system moving under the influence of conservative forces takes the path for which the action has an extremal value, a minimum or a maximum. Now, what is the action? Well, there was considerable debate over what the action was supposed to be. So I'm going to butcher this name, Maupertuis, who was the original proposer, the person who originally proposed the PLA, although some say it was Leibniz, but it seems to be him. He proposed that what's being minimized is what he called the vis viva, which is roughly the kinetic energy of the system. The modern formulation, again, due to Hamilton, takes the thing, the action, the thing that's minimized, to be the difference between the kinetic and potential energies, also known as the Lagrangian integrated over time. So S here is the action, and we're just going to take the for some entire path, we integrate over that path the difference between the two, and we try to find the extremal point. So somewhat more accurately, the principle of least action states that for small variations in the path, the first order change in the action vanishes, right? If you remember your calculus, if you have a function, you can find the minimum or the maximum by looking at the slope of the line and finding the place where the slope of the line is 0, at least to first order in the Taylor expansion, right? So that's the somewhat more careful definition, is you make a little change and it doesn't make any difference to first approximation. Okay, so right, so there's another way of stating that. You take the derivative and it's stationary to first order. Some people call the principle of least action the principle of stationary action. Is perhaps more accurate, but I'll just stick with the historical name. Okay, so again here, I'll just borrow from Feynman, his very helpful graphical explanation here. So suppose you have a system going from here at time 1 to there at time 2. Which path minimizes the action? Well, suppose first you got no forces involved, no gravitation or anything, and you've just got space in the vertical dimension, time in the horizontal. If the particle is moving all around, that's going to require a lot of energy, right? You're going to have to get it moving this way and then moving that way and then moving that way. You're going to have to put a lot of energy into the system. So that's not the least action, because the action term, remember, is kinetic minus potential. There's no potential here, so it's just kinetic energy. So what is the most efficient path? Just a straight line if there are no forces involved, right? That's the one that's going to minimize the action because it minimizes the kinetic energy. So that's an example of how it works in the simplest case. Now, what happens if we have a force like gravity involved? Here we are going to get, as we know, a kind of parabola shape. It's going to go up and then down. How is that consistent with the principle of least action? Well, the idea is that it's good kinetic energy you should minimize, but you also want to maximize potential energy because that's subtracted. So the thought is, if you throw the object kind of up and it comes down, you get the right balance of kinetic and potential energy. You don't want to accelerate it too much because that would take a ton of energy. You don't want to go really high, but you want to do just enough that the potential energy starts to kick in and finds the right balance. And in fact, this is the shape you get, which is the one that we expect from Newtonian physics. All right. So as this indicates, in fact, the principle of least action is equivalent to Newtonian mechanics, or here's how Feynman puts it: the laws of Newton could be stated not in the form F equals ma, but in the form the kinetic energy, the average kinetic energy less the average potential energy is as little as possible for the path of an object going from one point to another. So he's seeing this, and a lot of physicists talk this way, is seeing this as basically just another way of formulating the laws of classical physics. So I'm not going to go through it because it's a bit tedious, but to give you a rough idea of how this equivalence works, suppose we have a particle moving in a gravitational field with a certain potential. Then we can write its action, as I said, is the kind of integral of the potential minus the kinetic minus the potential energy. When we write that out, we get this expression over here, the 1/2 mass the dx dt squared minus Vx. So that's the kinetic energy term. That's the potential energy term. And then what we can do, and this is what Feynman does in his explanation, is you consider the action of the actual path, call that Sx, and the action of a path that's slightly different, Sx plus some small eta. And you want that to be 0 to first order. That's what the principle of least action says. And then you do a little bit of a tedious calculation, and you can end up with this result that the negative mass dx dt squared minus dv dx is stationary, is 0. And when you reconfigure that, you get this, which is just F equals ma. Now, I know I've left out a lot of that, but hopefully you can sort of get a flavor of how this works to show that they're equivalent. Okay, so although, and again, this wasn't clear at first, so again, I'm being very anachronistic here that these two were equivalent. But now that we know that, we could just view the principle of least action as a kind of superstructure rather than an explanatory principle. So again, it's up to us which way we take the arrow of explanation to point. So here's Lagrange, another very famous physicist. I view the PLA not as a metaphysical principle, but as a simple and general result of the laws of mechanics, right? So it could just be a generalization. But again, as with Fermat's principle, there's another option. We can regard the principle of least action as a more fundamental principle to which the dynamical laws of classical physics must adhere. And there's a certain, I think, important explanatory power in doing so. Okay. Okay. So now let me say a little bit about the Feynman Path Integral formalism. The basic idea here of the Feynman Path Integral formalism is to sum over all the paths of the system through state space. So even in principle of least action, we were talking about state space, but I kind of glossed over that. Associated with each path is a probability amplitude, and then at the end we add those together. The resultant amplitude allows us to determine the probability of the end state. So here's a picture. There it is. So we have state A, state B. We consider all the ways to get from state A to state B. Each of those gets a wave, a probability amplitude. We combine all of those, and that tells us how probable B is. Okay, that's the basic picture. That's all really you need to know about that. Now, I mean, and you can already see the connection here with principle of least action. It's a very similar picture to what we had. We're considering all the possible paths and in some way adding them or picking out some of them. Okay, so there's an important, again, being anachronistic here, I'm out of chronological order. There's an important result that Dirac established in 1933, that there's a connection between the probability amplitudes of these paths and the action. In particular, the probability amplitude of a given path is going to be represented by a complex number that's proportional to this quantity, e to the I s over h bar, where h bar, s is the action, which we've already talked about. H bar is the Planck's constant, which tells us when we're kind of in the quantum regime. Okay, so in other words, the phase of the amplitude is proportional. So this part is called the phase. So you could say that the phase angle is s over h bar, is proportional to the action. So this is going to allow us to derive the PLA. So when the action is very large compared to h bar, so that means we're in a kind of classical regime, the paths with different actions will have amplitudes that are really, we'll have phases that are really different. So the amplitudes will be out of phase. And when you have waves that are out of phase, they cancel out, they interfere destructively, right? So the amplitudes cancel out, leaving only the values of s that are very close, equal to first approximation, which will sum. So again, the picture here is any of those paths that have very different actions will sort of be constantly very different in phase. So because we'll be dividing by this tiny number, this really big number. So we'll get a big difference in phase. So that means they're not going to line up and they're all just going to kind of wash out. So we'll just have one left. So as h bar goes to 0, so that's kind of the classical limit, the probability goes to 1 for a path where S doesn't change to first approximation, which is just the PLA, right? It's saying the derivative of the action is 0. Okay, so here's what Feynman says in a picture. In the limiting case in which Planck's constant goes to 0, the correct quantum mechanical laws can be summarized by simply saying, forget about all these probability amplitudes. The particle does go on a special path, namely that for which S, the action doesn't vary to first approximation, which is just the principle of least action. So we get a privileged path, which is the same path that classical physics gives us because all the others cancel out. All right. So we can derive the PLA as a limiting case from the Feynman path integral formalism when the action is much greater than h bar, namely we're in the classical regime. So here's a contemporary philosopher drawing the connection I mentioned earlier. So this is in his book on causation in physics. Ben Menahem says, it's here for the first time that the principle of least action is given an explanation that completely defeats the teleological interpretation that had accompanied it for more than 2 centuries. Right. So that's what I'm not sure. Like I said, this is sort of a newer topic for me. I'm not sure exactly how widespread this idea is, but it seems to be the case that a lot of people think, to the extent that this derivation I just mentioned works, it shows that we shouldn't be worried about teleology and PLA. So that's what I want to kind of push back on a bit in this next part, the assessment. Okay. I take it the argument's something like the following. So the PLA provides an explanation that's at least teleological in some sense. There's some kind of a goal state supposed. But the PLA is explained by Feynman Path Integral, which is non-teleological in nature. So the teleological aspect of the PLA explanation is dissolved. This is very schematic, but I think something like this are the key claims. So like I said, I want to kind of put pressure on this. I think there's some issues with each step here. So one issue concerns the status of the explanation that PLA provides. So think about the Feynman Path Integral, sorry, the status that the Feynman Path Integral provides. So unlike the Huygens explanation of Fermat's principle, these paths are virtual. Okay, so there's nothing traversing these paths through phase space or through state space. They're just ways of figuring out the actual path, right? And so a lot of philosophers have picked up on this kind of modal aspect of the laws, and that's a whole nother kind of interesting debate on this. But the point I want to make now is just that it's not clearly causal given that. So right, it's not clear that interference of probability amplitudes is an adequate basis for causal explanation. I have scare quotes there because it's not even clear how we're supposed to understand these things, these probability amplitudes that we assign a phase to and that interfere when we try to figure out, when we combine them to get that final probability. Feynman himself seems to view the virtual paths as instrumental, that is just a means for predicting the behavior of physical particles. But more generally, it's hard to know kind of what is the underlying metaphysics or interpretation of this path integral formalism. So that makes it hard at least to see this explanation as an ontic explanation. Maybe it provides an epistemic explanation, but it's not clearly a causal explanation, let's say that. There are also general concerns about explanations by means of a limiting case. So remember, this explanation that I sketched only works kind of at the classical limit or as we approach the classical limit. And there are general worries about this that are well known in the philosophy of science. So, I mean, one thing, we never actually reach the limit, right? We never actually have a case where Planck's constant is 0. If we did, in fact, that wouldn't work because the action over h bar would be undefined. So we're dividing by 0. There's also a point due to Kuhn and others that in these limiting cases, we don't actually recover the explanandum, that is the principle of least action, but something that's formally equivalent to it. What do I mean by that? Well, in this case, the version of the principle of least action we derive as a limiting case from the Feynman path integral is still expressed in quantum theoretic concepts, the phase of a complex valued probability amplitude. So again, we might worry that what we have is sort of isomorphic to the principle of least action, but couched in terms of different concepts. So I think there are some worries about the derivation here, or the explanation. Even if we grant the legitimacy of the derivation of the PLA from the Feynman path integral formalism, I think we still might say that it doesn't sanitize it of teleology, right? I mean, there's one sense in which none of this should be surprising. Given that the PLA works in classical contexts, we should expect the Feynman path integral, or indeed any account of quantum mechanics, to agree with it at the limit, right? So there's nothing kind of revealing about that fact. So I don't think that, to some extent, the derivation doesn't make the explanations based in PLA any more parasitic on the Feynman path integral than any non-quantum principle is. I mean, I take it that if you think there's teleology involved in, say, evolutionary biology, then the fact that there's no teleology in quantum physics would be neither here nor there, right? These higher level principles, even though in some sense they're going to depend on the fundamental microphysics of our world, it's not clear that that sort of diffuses any aspects of those explanations because they're in some sense non-fundamental. And yeah, moreover, we might recognize that the principle of least action has a certain degree of autonomy from the more fundamental quantum theory, even if the latter can be used to derive the former. What do I mean by that? Well, you can vary certain details in that story that we told from the Feynman path integral approach, and without disrupting the explanation, right? We could have it be the case that, for instance, we change the amplitude slightly, we change the constant that's involved in the phases. It wouldn't change much if we slightly altered any of those things. All that matters is this very general fact that the phase is proportional to the action in the way that I sketched. So there is a certain degree of autonomy, which is, again, something we often see when we're looking at higher level explanations. People who talk about emergence in physics often point to this fact. Okay, so I think there's good grounds to think the derivation notwithstanding, the principle of least action should still be regarded as a legitimate explanatory principle in physics. So I guess the interesting question for those of you in the audience who care about teleology, where does this leave us with respect to teleology? And again, here, my conclusions are pretty tentative here. I think the kind of most literal understandings here are problematic. But if you think otherwise, you can convince me in the Q&A. I don't think we should say, as Feynman put it, that the particles somehow sniff out the correct path, that we shouldn't be attributing mental states to particles, unless you have independent reasons to be a panpsychist or something. The other thing I haven't mentioned yet is some of the early discussions of PLA describe it in the context of a kind of efficiency of nature. So this is, I guess, going back to the classical understanding of teleology as a kind of telos, as the universe being as simple as possible, or obeying certain certain orderly principles. That doesn't quite work because we've been talking about the principle of least action, but again, as I've mentioned at several points, the demand is that the action is an extremum. So it could be a minimum or a maximum. So there's at least a problem in a prima facie problem with saying that this is a way of articulating a kind of efficiency of nature, that nature is using the least amount of energy possible or something. That won't work, at least not straightforwardly. So there are some problems, I think, to the usual kind of naive ways of thinking about teleology here. But I think it would be an overreaction to conclude that these explanations are merely heuristic or epistemic in nature. So I don't think, as some people seem to, that the principle of least action is just sort of pedagogically useful or useful for giving you the flavor of how physics works. I think there is more to be said in its favor. Okay. Oh yeah, so back to Nagel. Here's a kind of example of a deflationary take. So later in that same book that I quoted earlier, he talks about the principle of least action. He says the use of variational principles in physical sciences, nevertheless, does show that the dynamical structure of physical systems can be formulated so as to make focal the effect of constituent elements and subsidiary processes upon certain global properties of the system taken as a whole. So he thinks there's some value in variational principles, but notice the order of explanation here. It makes focal the effect of the constituent elements and subsidiary processes upon the global properties. So clearly for Nagel, he's thinking that the order of explanation goes from the kind of microphysics or the dynamical laws to the variational principle rather than the other way around. And again, I just think there's good reason to resist that. I think often in physics, we're more interested in these general principles, or we give them a kind of more fundamental status than the particular instantaneous laws that we have. So I think this is too weak. So I want to now invoke Leibniz here for a slightly more thicker notion of what final causes, or sorry, what PLA might be telling us. So here's Leibniz in a work called On Nature. Final causes not only advance virtue and piety in ethics and natural theology, but also help us to find and lay bare hidden truths in physics itself. So I think there's something to this idea. I think there's something in nature that is being picked out by teleological explanations in physics. I'm not clear on exactly how to articulate that, but I think this is on the right track. So let me just conclude with, like I said, some kind of speculative thoughts here. So clearly variational principles have played an important role in physics, despite their teleological character being at odds with the dominant form of efficient causal explanation. The derivation of variational principles from dynamical laws often fails to determine the direction of explanation. So I think we could take it either way. And in particular, the fact that the Feynman Path Integral formalism and the PLA agree at the classical limit is compatible with the PLA serving as an autonomous explanatory principle in physics. Again, autonomous here, I just mean it doesn't depend on the specific details of the underlying microphysics. So I think there are reasons to think that PLA is tracking patterns of dependence in physical reality that go beyond those found in the dynamical law to some extent. So I think that we can say more than Nagel says. It's not just that the dynamical laws, we can generalize some more general patterns by looking at the dynamical laws. It's rather, there are these real metaphysical dependencies in nature that are being captured by these principles. And those are in some ways, again, something over and above what we see in the fundamental dynamics. Okay, so that's all I've got. So thanks a lot.